I notice that sometimes I move in front of the board, and I'll try and stay out of the board so you can probably see it better. Today we're going to try and discuss the diffusion equation and consequences of the diffusion equation and why that's extremely important. We have within applied math. So we have applied math. We have applied mathematics, and within this, within applied mathematics and looking at differential equations, we also have things known as tensors. Now, in looking at a lot of stuff, there are experts, and Werner, you're top-notch in this, of course, with tensor analysis. My time has been mostly spent in the world of applied math, so looking at them as two different views. Within tensors, we find certain things like stresses, strains, and so forth within a particular region. Applied math is usually applied within vector calculus and so forth. Within applied math here, we have basically, three, go into applied mathematics, there's really only three formulas that rule the world. They are psi dot equals del squared psi, known as the diffusion equation. This is the diffusion equation. Harmonic equation, also describing waves and so forth, equals del squared psi. This is from Hooke's law. This is the first order differential in time, second order differential in time. That's the dots mean, del operator. So this is now the harmonic equation, which deals like elasticity and so forth from Hooke's law, springs, etc. And the less well known, but it's used quite a lot, del to the fourth chi equals 0. Now this one here is the biharmonic formula, which we were using in earthquake prediction and other things like that. Okay, now to go through this more, this item here becomes rather important. So if I may look at this. Del squared chi is the Laplacian of a scalar potential field psi. That is the Laplacian. Del squared psi equals 0. The space is flat. Okay? This is the curvature of the space, denotes the curvature of the space. The difference between gradients as we go along. If that's equal to 0, it is flat. Not equal to 0, it's curved. Okay? So we have curvature that's not equal to 0. Therefore, if we have something which says del squared chi equals 0, and then we give it some misnomer like the time-independent Schrodinger equation, for example, del squared chi is equal to 0, the space is flat. Nothing can happen. There's no curvature to allow anything that can happen. There can be no event mathematically described by that particular equation. So I'll now go into the diffusion equation, which, as we all know, psi by dt equals del squared psi. Please forgive me for the units, constants, get the units right. But nevertheless, use Fick's law, which says the flux goes through a certain region, a certain amount of stuff that passes through a certain region is proportional to the gradient. So if we have a gradient of psi, and psi is a concentration of material, we're talking about diffusion, stuff diffusing into something else. Concentration of material that diffuses into a particular region is proportional to the gradient, and coming out would of course be proportional to the gradient coming out, or del of psi, or what is the difference between them. So the difference between them in each region, the del squared of psi. The curvature that we have here is equal to the rate of increase, or decrease if you like, of the amount of material in that particular region. So that's Fick's law that describes the diffusion equation. Now something happens with the diffusion equation as a consequence of this. Quite often we may think that as something, let's say we had something and it's going through a region, we'll think of a number of particles that are going into this region of one substance to another substance. So it could also be temperature. So we're thinking of molecules that are moving around faster and faster and so forth, with things like that. But if we look at the solutions to the diffusion equation, something entirely different starts popping up. Some strange stuff that we don't talk about with the diffusion equation. You know, it's doing its thing. So if we have a solution to it, let's say we have a barrier, a substance on one barrier, and a different substance on the other barrier, a dark substance, and this substance is going to diffuse into this area. Okay, we remove the barrier, and it goes away. This stuff is now going to diffuse into this area, and we will use the diffusion equation to allow this stuff to diffuse forward into wherever it is here, and we'll make it a finite region with a bar at the end here, and then we'll take concentration profiles afterwards to see what the concentration profile of this substance into this substance looks like, using psi as the concentration per whatever, could be kilograms per liter, or weight fractions, or things like that, or temperature. Now, if we look at a graph, let's say at a particular time, at the very beginning, at time equal to 0, if this is x equal to 0, at the barrier, and the back end of it, saying x, let's call that r, at this back region. Now, if we release it, at the very beginning of time, we have this concentration profile. It is a certain amount here, psi naught at the beginning. We release the barrier, and it will diffuse forward. At a nanosecond, at less than a nanosecond, instantly after the barrier has been moved, the profile will describe like this, and there will be some substance down at the far end. Instantly. This could be huge, miles and miles away. Mathematically, remove that barrier, instantly stuff is at that end, faster than the speed of light. It just instantly happens. One of the properties of the diffusion equation, I mean, this is a continuum. We're dealing with continuum, not atoms here, but this is a mathematical continuum. If we are dealing with the diffusion equation, stuff just happens. It may happen faster than the speed of light. There's no even stuff happening at the speed of light. It just happens. It's just an event that occurs. So we take a particular time period that has happened instantaneously afterwards. This is now the concentration profile. You do experiments, you find out it fits beautifully. After a period of time later, you'll get concentration profiles like this. Let's say the boundary is not moving in, and you would then have diffusion moving through. But each line segment is instantaneous, or can be thought of as instantaneous. It just happens. This is a property of the diffusion equation. If we have harmonic equation, stuff happens according to a particular speed, according to the Young's modulus and so forth, defined by the substance and the harmonic equation. So as the harmonic equation means, stuff will move, the waves will move at a particular speed. This is not dealing with waves. This deals with, yes, we have cosines, sines, other things with it, but this is not describing something that is described by waves as is the harmonic formula. What is being described is the diffusion of one substance into another substance, or temperature changes and so on, according to this particular formula. This is not Schrodinger's equation, it's diffusion equation. Schrodinger's equation is plus some constant times psi. We got some constants there, h bar, I, etc. h bar squared twice m minus I. So now we got Schrodinger's equation, but it is based and has the properties, or some of the properties, of the diffusion equation here. And that's why when you start trying to take apart anything within the region you don't know about, as we described before, once you get into the Heisenberg boundary condition and so forth, here, once you're into, let's say, quantum space, Q, the big Q, if we're into that particular quantum space, you can no longer use the models, the physical models that you used previously, regarding things that deal with the harmonic equation. This is stuff we see on a more gross scale. This is what we start to see on a minute scale. We don't actually see it. It just happens. You have a before and you have an after.